After you've collected all your data, what do you do with it? The main technique you'll learn in this video is how to compare rates. Rate comparison is my pick as a first statistical test to learn in HCI because it's easy to do and relevant to many real-world activities, like comparing click-through rates on websites. Before we get to the details, let's begin at a higher level. Here are 3 really important questions that you can ask and answer by analyzing your data. For starters, what does my data look like? To do this, explore your data graphically, plot all of your data, and then, once you see some patterns that may be interesting, try to look at aggregate summaries of different sorts. Second, after you've looked at your data graphically, what are the overall numbers? These aggregate statistics help give you a quick summary of what you've seen in your experiment. Simple things to look at initially are mean, the average, and the standard deviation, how much variation was there within each condition. And third, are the differences that you see in, say, the means real? Separating real differences from mirage differences is the goal of statistical testing, and you'll learn a technique for doing that in this lecture. Say, for example, I have a coin, and we'd like to know whether it's loaded. That is it equally likely to produce heads and tails? So I have a coin right here, and I can toss it a whole bunch of times. Tails, heads, and I can keep going. Let's say I toss it 20 times, and 13 of those 20 tosses turn up heads. What would we expect to get? Well, if we have an even coin that is equally likely to produce heads and tails, that would say that our expected value for 20 tosses would be 10 heads. Is 3 extra heads out of 20 a significant difference? That is it weird enough that we would be pretty likely to say that our coin is biased and not an even coin? Well, to figure this out, we're going to use a test statistic. And what attributes does our test statistic need? Well, one thing that we'll want to encode is the difference from the expected value. So the fact that we got 3 extra heads here. And we want to know out of how many this is out of in a couple of ways, both in a ratio sense. 3 is less material if it's out of 1,000, and also in a number of trials sense. If we had 1,000 trials and we saw a 30% rise in the number of heads, we might say that that's more unusual than if we had a couple of trials and had a 30% rise, because that's only a few. And so in this lecture, we're going to use the Pearson's chi-squared test. This is a fancy name for the totally standard test for being able to compare the rates of an expected value to an observed value. And it's going to use exactly the parameters that we decided were necessary. So it's going to compare our observed to our expected, and it's going to do that in a way that as we have more trials, if we have a sizable difference, that will give us increased confidence that the difference is robust and significant. And it's called the chi-squared test because the value that we're going to get out of this test is called the chi-squared value. So our chi-squared value equals, we're going to take the difference between the observed and the expected value. It's always positive so that a divergence in either direction is positive, and also so that large divergences from the mean are more notable than smaller ones. And then to get that as a proportion, we'll divide that by the expected value. And we're going to consider this difference for each of the possible outcome values. In our coin, we only have 2 values, but you can imagine a dice or other options where there would be more possible values of the outcome. Now, before we get to the outcome of our test, I'd like to introduce some additional machinery first. You can imagine that a normal coin, one that's not loaded, will, if you toss it 20 times, sometimes it'll come up 10 out of 20, right at expected value, but it wouldn't be shocking if it came up 9 heads out of 20 or 11 heads out of 20. And this distribution of expected values for something like a coin will follow what's called a normal or Gaussian distribution. So you've got the expected value or the mean in the middle, and that's going to be the most probable outcome. And then it's going to slowly fall off, becoming increasingly unlikely as you head out towards the tails. And the area under our hill is going to sum to 100%. The sum of all the possible probabilities adds up to 100%. And out here on the ends are the two tails. And we're going to call the area that's in those very edges the really unusual behavior. So to fill this in a little bit, in our coin case, our expected value is going to be 10. So our mean will be 10. And we'll have some observed value. Here in our example, 13. And the question that we're going to ask with our statistical techniques is whether that observed value of 13 is sufficiently weird, whether it's sufficiently far out into the tail as to qualify as unlikely to have occurred by chance. And that hinterlands of unlikely to have occurred by chance, by convention, we're going to have be the portion of the two ends of the tails that together forms 5% of the distribution. This would be for a two-tailed example. And so if you've ever read in a scientific publication that the probability was p less than 0.05, that p-value is this observed value that we're seeing. And if it falls out far enough out in the tails, we're going to say that that was unlikely to have occurred by chance. The second piece of machinery that we're going to need to be able to do our statistical test is an idea called the null hypothesis. And what the null hypothesis means is that our opening bid in any statistical test is going to be, we don't think there's a difference between the two conditions, or however many conditions you have. So in the case of our coin, what that would mean is your opening bid would be the null hypothesis, which would be the coin is not loaded. Or to be a little bit more precise about it, the behavior of the coin does not differ significantly from that of a normal unloaded coin. And what our statistical test is going to do is we're going to check whether the data falsifies the null hypothesis. So that's a fancy way of saying that if our opening bid is this coin's behavior doesn't differ significantly from a normal unloaded coin, and you got, say, 20 heads out of 20, you'd reasonably say, this isn't right. So in that case, our data would allow us to say that we've falsified the null hypothesis in this case, that we reject the bid that the coin's behavior is normal. And the very last thing that we're going to need out of our statistical test is, in the case of a chi-squared, we're going to need to know what's our p-value, what's the probability that the observed behavior could have been generated by a normal coin. So as our probability goes down, as it becomes extremely unlikely that the behavior was generated by a normal coin, once we get past our magic threshold of 0.05, we're going to say, we reject the null hypothesis, that's a loaded coin. So the thing to take away from this table is that as your chi-squared number gets bigger, as that gap between expected and observed gets larger, or the number of trials gets larger, that's going to up your chi-squared, and in turn that's going to make it increasingly unlikely that this behavior could have been generated by an unbiased coin. So now we can return to our example and do so a little bit more formally, and we can ask 20 tosses, 13 heads, at p less than 0.05, can we reject the null hypothesis that there is no difference between this coin and an unbiased coin? So let's work it out. We've got 13 minus 10 squared over 10. Those are our heads, the 13 observed minus the 10 expected. And then we're going to add the other side of the coin, which is 7 observed tails minus 10 expected tails, again squared and divided by 10. When we sum that all up, we get a value of 1.8. The other thing we need to figure out is the degrees of freedom. The degrees of freedom is the number of choices that you have minus 1. So for a coin, we have two sides, so it's two choices minus 1 gives us 1 degree of freedom. And that's because, you're really only picking one thing. If you had a die, for example, a 6-sided die, your degrees of freedom would be 5, because there are 6 faces minus 1, that gives you 5. So we can go to our table, and remember, as we go further to the right, that makes it unlikely that we have a normal coin. So that's our loaded coin. And with 1 degree of freedom and a chi-squared value of 1.8, we can see that we have coin behavior that is slightly unusual for an even coin, but not out of the realm of reasonable. It's between 10 and 25% of the time that you toss a coin 20 times, you'll see a divergence from the mean of this magnitude. And so because our divergence, because our chi-squared statistic doesn't show up as sufficiently unusual, that is to say it doesn't make it to the 0.05 level, in this case we can't reject the null hypothesis. So that's a real fancy way of saying that we can't yet stand up and say this coin is a loaded coin. If we really cared, the thing to do would be to gather more data. So let's say we keep going. We're going to now toss it 60 times. And we see this same ratio continue. 39 out of 60 times it shows up heads. So that's going to give us 39 minus 30 squared over 30. That heads, plus 21 minus 30 squared over 30. That's our tails. And that's going to give us a much bigger chi-squared value. Even though the ratio is the same, because we're having more trials, that's increasing our confidence, and the chi-squared value goes up. So now it's up to 5.4. And we can look up in our table, again, same coin, still a coin, so degrees of freedom is still 1. But we see now that our chi-squared value is way over to the right. And so the equivalent p-value that pops out of this table is somewhere around 0.02. So we can reject the null hypothesis that our coin is no different than an unbiased one with 98% confidence. One thing I'd like to point out is that if your trend is robust, if the ratio continues, increasing your sample size by, in this case, a factor of 3 is going to decrease your p-value by a factor of 9. So that's all well and good, you might say. You now know how to walk into a gambling hall and check whether the coin that somebody presents you with is fair or not. But what does this have to do with HCI? Well, the mechanism that we've just learned for comparing rates that holds for coins also holds for things like click-through rates on websites. Let's say we have a website that has a button labeled sign up, and 10% of visitors click that button. To try and improve traffic to that button and get more conversions, we might change the button to learn more and then start gathering data. Over a week, there are 1,000 visitors to the site, and 118 of them clicked on the learn more button. Can we say with confidence that the learn more button has a higher click-through rate than the sign up button did? So we can work it through. We have 118 observed clicks on this site minus 100 expected clicks on the site, and we have 882 people who did not click minus 900 who we expected would not click. And as you can see, over a week there were 1,000 visitors to the site, and 119 of them clicked the Learn More button. Can we say with confidence that the Learn More button has a higher click-through rate than the Sign Up button? Let's work it through. So we have an observed number of, so we have 119 observed click-throughs minus 100 expected, and we have 881 observed non-clicks minus 900 expected. Add it all up and you get about 4.01 as the chi-squared value. And again, we have 1 degree of freedom because we have 2 choices, clicked and didn't click, 1 degree of freedom. And when we look it up on our table, what we see is that the chi-squared value is just slightly larger than the threshold for p less than 0.05. And so we can say that this change indeed probably did influence the click rate. So the chi-squared test, and statistical testing as a general methodology, gives you 2 really powerful tools. First, it gives you a way of formalizing, we're pretty sure. And deeply intertwined with this is it gives you a way of generalizing from small samples. Are the differences that I've observed on a small scale likely to generalize if I were to scale this up? And this idea of inference from small samples owes a lot to beer. In 1908, William Gossett was a chemist at the Guinness Brewery in Dublin. At the time, Guinness was hiring top graduates from Oxford and Cambridge to apply biochemistry and statistics to Guinness's industrial processes. And Gossett devised the t-test as a cheap way of monitoring the quality of stout. He published this test in Biometrica, but he used a pen name in the journal so that Guinness could keep its use of statistics as a trade secret. For Gossett and Guinness, there were really two important benefits of being able to make broad quality estimates from small samples. First, if Gossett's testing consumed all the beer, there would be none left to sell. Second, many statisticians find it difficult to do mathematics after having consumed a large quantity of Guinness, and so the quality of the results are importantly contingent on testing on just a small sample. And this general strategy of working from a small sample and performing significance testing can be done under a variety of frameworks. So today we talked about the chi-squared test, but there are several others. For example, if you have continuous data as opposed to discrete rate data, there's the t-test. And if you have more than two conditions, there's a test called the ANOVA, or the analysis of variance. And these all work for the same normal Gaussian data that we've been looking at so far. So for example, these tests can help you compare which vacuum cleaner gets things cleaner, if you have a measure of cleanliness, or which running shoes help you run faster, or which input device, trackpad, mouse, stylus, is fastest for input. And while handling it is beyond the scope of this class, I think it's important to point out that data often isn't normally distributed. Data could be bimodal, so if everybody falls into one of two camps and nobody in the middle, then you don't have the nice big blob for a normal distribution. Or it might be shifted over to one side. For example, anything that's time-based. You can be infinitely slow, but you can't be infinitely fast. And right now, I just wanted to point out that that's something to watch out for. In practice, a lot of the tests that you'll come across are reasonably robust to modest deviations from being normal. And so, especially for practical purposes, things often work out. And so knowing what those assumptions are and whether a particular test is appropriate for your data is half the battle. Another clever technique that I picked up from Ron Kohavi is to use AA tests, which is to say, take one condition, like all of the people who got the sign-up button, divide that in half, and see if you see a statistically significant difference between one half and the other half. That can be a good warning sign about whether you're seeing mirages. Or, and again, this is way beyond what we'll cover here, you can use techniques like randomization testing, which make no explicit model of your underlying data and rely on repeated simulations as a way of modeling the data. So, to pop back up, what we learned today is that to get a feel for your data, graph it all. We also saw how statistics offers us tools that help you distinguish real trends from mirages. And we learned a common technique, the chi-squared test, for comparing rates. And here, as with other lectures, my goal was to provide you both with an introduction to an area and a concrete skill that you can put to regular use. The web has provided huge increases in the quantity of available data and also made it much easier for you to run experiments online. So my hope is that many of you will use the experimental skills you've learned here all the time. And while there's nothing fancy in this video, you may find it helpful to review it once or twice when you first use them for your own work. And really, we've just scratched the tip of the iceberg. If you'd like to learn more, as a next step, I highly recommend Jake Wabrock's course on practical statistics for HCI. He's got a series of online materials. If you'd like to learn about practical strategies for doing experiments in a general sense, I highly recommend David Martin's Doing Psychology Experiments. If you'd like to learn about the philosophy behind statistical testing, there's a great book called Statistics as Principled Argument. And if you'd like a nice flow chart of which test should you use when, I recommend the book Learning to Use Statistical Tests in Psychology.